All right, we're starting chapter 4. So we do 3 sections out of chapter 4. These are relatively quick individually, but they do take some time and they will take some practice on your part. It's all about systems of equations. So 4.1 is solving systems of linear equations in 2 variables, specifically by graphing. Now we are going to kind of get a lot of the definitions and stuff out of the way in this section. I will repeat them in the following sections just so they're there as you're working on them. You can remind yourself. But this one's going to be the longest of the 3 in terms of the definitions and things. But we have 2 objectives in this section. The first is to determine when an ordered pair is a solution to a system. And the second is to solve systems by graphing. So, systems of equations are defined by when we group 2 or more equations together by some relationship. We call these equations a system. And a classic example, my system got a little crooked there. A classic example is supply and demand. So these curves are always linked because they always affect each other. And that's kind of what we're talking about. Now, there are systems with 3 equations, 4 equations, 5 equations. We will be exclusively looking at systems of linear equations in this chapter that only have 2. And I do want you to note that nonlinear systems do exist. I can't remember off the top of my head if we'll be looking at any nonlinear systems in future chapters, but they do exist, and they are something that gets studied fairly widely. So let's look at a couple examples here. This is just 3 examples. Standard linear equations in standard form. We have a vertical equation and an equation. We have a horizontal equation and an equation in non-standard forms. So it's just 2 linear equations. You have to have at least 2 variables when you are talking about them. You have to have an x, you have to have a y. So now let's talk about solutions to systems of equations. There are 3 potential answers when we're discussing systems of equations, systems of linear equations in 2 variables. The first is we can have one solution, i.e. an ordered pair. We can have infinitely many solutions. Or finally, we can have no solution. So we will be talking primarily about the last 2 in this section, not because you can't get a one solution system with graphing as your solution method. It's just that graphing is, in my opinion, the least accurate of the 3, and typically you want to save graphing as your last ditch effort if you can't get through the other 2 methods in the next 2 sections. However, for these 2 solution types, infinitely many and no solution, graphing actually showcases when that happens very, very well. And so that'll be what we focus on. It's not entirely what we will be focusing on for the remainder of the chapter, but this section will rely heavily on it. So in this example, we're just going to start with determining when an ordered pair is a solution. So determine whether or not the point -1, 1 is a solution to the given system. So to do this, you just plug in your point into each equation. So we have negative times a negative 1, plugging in for x, plus 1 should equal 2. Negative negative makes positive. 1 plus 2 is 2. And plugging into the second equation, we have 2 times negative 1 minus a positive 1 should equal negative 3. Negative 2 times negative. Let me try that again. Third time's the charm. 2 times negative 1 is negative 2. Minus 1 does indeed equal negative 3. So our answer here is yes, it is a solution. So then, flipping the page here, in the next example, we have determined whether or not the point negative 2, 3 is a solution to the given system. Again, it's the same process. Plug this point into each equation. So we have 5 times a negative 2 plus 3 times a positive 3, and this should equal negative 1. This is negative 10 plus 9, which does indeed equal negative 1. And plugging into the other equation, we have negative 2 minus 3 should equal negative 1. But this is negative 5, and so this does not equal negative 1. And so the answer here is no, this is not a solution. So, like I said, in this section we're going to be going through most of the definitions, so that's what this next box is. But when you're determining points, whether points are solutions or not, this is the way to do it. Just plug it in, check both equations. Easy peasy. So as far as solving systems goes, now that we know how to check if we have the right solution, there are 3 techniques. The first is what we're talking about in this section, which is graphing. And as I said a minute ago, this I think is the least accurate and the least useful. The second is what's called substitution, which is what section 4.2 is all about. And the third is elimination, which is what section 4.3 is all about. And I'm sorry about that. That was my doorbell going off. So we're going to solve systems in this section by graphing. So we're going to start with this problem. X minus 2y equals 4 and x equals 2y. So essentially this comes down to, we're going to graph equations, just like we've been doing. So the first thing I'm going to do is scale my axes. I guess I'll go out to 8 on the x. Scaled by 1s. And we'll go down to negative 6. That's supposed to be a 4. Go up to positive 6. Okay. So we can use any of the techniques for graphing linear equations that we've looked at in the previous chapter. So whatever your favorite technique was, employ that for both of the lines. For me, I like intercepts. So I know my intercept of line number 2 is 0, 0. And then I'm just going to plug in x equals 1 to get 1 equals 2y or y equals 1/2. So I have 1 1/2 right here. And then a nice straight edge to make the line. So this is, I'm going to label this 1 and 2. This is line number 2. And then for line number 1, I'm going to solve this real quick here for y. This is negative 2y equals 4 minus x, or y equals x, or 2y equals x minus 4. So y equals 1/2 x minus 2. So that gives me an intercept here. And then I can plug in, actually I think I'll use slope on this one since I have it, up 1 over 2. That's right here. And we can make a nice line. My scale is not perfect here. But you can see, I know I messed up my scale a little bit, so maybe it doesn't look like this exactly, but what you should be seeing is that these look parallel. They don't cross. So if you go back to that first page in this packet, if you're going to have one solution or any solution, they have to cross each other and intersect. Well, these don't intersect, which means there are no solutions. No solutions, because they're parallel. And I could have solved this equation here for y equals 1/2 x to see that they have the same slope, so I know that they're parallel. Again, using properties from our previous sections, previous chapters. So this is what happens geometrically when there are no solutions to a system. It means that the two lines are parallel to each other. Now, to talk about systems a little bit further, we do classify them based on their solutions. So we have two ways in which we classify systems. We classify them as either one, consistent, which means that there's at least one solution, or two, inconsistent, which means there are no solutions. And so the last example, that was an inconsistent, with a T, system. It had no solution. So when you have an inconsistent system, it means that your lines are parallel when dealing with equations of two systems of two equations of two systems. Okay, so we have another example here. Solve the system by graphing. So this is the same problem, or the same graph that we had in the first one. On this example here, it's x minus 2y equals 4. So I can graph that one quickly here. So I'm just going to do a rough scale. I'm not going to go all the way out, just to 4, 5. -2, -4. And I'm scaling this way and not going all the way out because I know that first line matches these points at -2, 0, and 2, -1. So we have -2, 0, 2, -1. So I can graph that line. And then now I'm going to solve this equation for y. So this is 4y equals 2x minus 8 by subtracting the 8 over and adding the 4y. And then y equals 1/2 x minus 2. Well, that's the same line. So I don't need to graph anything, because I already have both lines. This is both 1 and 2. Well, that means that every single point that we could ever have on this line is a solution. And as we know, there are infinite points on any given line because it stretches out for infinity. So this is infinitely many solutions. So geometrically, on the graph itself, when you have infinitely many solutions, it's because you actually have the same line. They've just been manipulated, right? This looks like 2 times all of the numbers of the first one. So you can multiply by 2, by 7, by 1/2, by 0.6. That's what infinitely many solutions means. You really don't have 2 lines. You have the same line, just in 2 different forms. Now, when you have lines of different forms, that is what we call dependent equations. So 2 equations are said to be dependent if one equation can be algebraically derived from the other. So if I multiply equation 1 by 2, 2x, negative 4y, and 8, I've algebraically manipulated it, and I have it equal to the second equation here. As we said, the previous example is a system of dependent equations. The solution of dependent equations is always infinitely many. So I've got a little shortcut thing here at the end to finish up this section. All the geometric interpretations. So as we saw in our two examples for this section, no solution is parallel lines. This is an inconsistent system, but it is still independent equations. One solution is an intersection of one point. Now we didn't see that in the graph because, well, I'm bad at scaling my axes, so it's really inaccurate to try and figure out the point. You'd just be estimating. It's still a consistent system because it has one solution and it's still independent equations. And then when you have infinite solutions, you really have the same line listed twice in two different formats. It's still consistent because it has at least one solution, but it is now a dependent set of equations. So those are our definitions, our base definitions, and how we graph to solve systems. In the next two sections, we'll be studying the two other solution methods, and all these definitions I'm repeating on the other two packets as well. So if these haven't sunk in yet, don't worry, you're going to see them again a couple times.